Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. I have the pleasure of facilitating today's event. This webinar focuses on DoD-funded research efforts to remediate sites impacted by PFAS and to identify PFAS-free alternatives to AFFF. We will have two speakers. First, Dr. Detlef Kenape from North Carolina State University will talk about his research to enhance PFAS mineralization during thermal reactivation of granule activated carbon. Detlef's presentation will be followed by a brief Q&A session. Then Dr. Braden Giordano from the U.S. Naval Research Laboratory will talk about the development of AFFF alternatives using polyethylene oxide-based polymers synthesized with reversible addition fragmentation chain transfer. Braden's talk will also be followed by a Q&A session, and we will conclude the webinar with a longer Q&A session featuring both of our speakers. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you could not download Zoom, you can view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you are unable to view the slides or if your screen freezes, try keying in Control and F5 to perform a hard refresh of your screen. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you continue to experience difficulties, feel free to call into the conference line shown here. You can also submit a comment using the chat box. Please use the chat box only for comments related to technical difficulties because the Q&A option should be reserved for questions for our speakers. And in case of continued technical difficulties, keep in mind that you can download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your webinar registration confirmation email. We will also be live streaming the webinar on the SERDP and ESTCP YouTube channel, and the link is also shown here. Today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A period to submit the questions. We do encourage you to get them in well in advance of the Q&A sessions. When you submit your question, we ask that you please add your organization name at the end of the question so that we can identify your organization during the Q&A sessions. With that, it is my pleasure to introduce Dr. Robin Nissan, who is the SERDP and ESTCP Program Manager for Weapons Systems and Platforms. Before joining SERDP and ESTCP, Robin worked at the Naval Air Warfare Center's Weapons Division in China Lake, California. Robin, please proceed.
Well, thank you, Rula. I'm very pleased to welcome everyone to today's SERDP and ESTCP webinar. In the next few slides, I'm going to provide an overview of SERDP and ESTCP. SERDP is the Strategic Environmental Research and Development Program. It was established in 1991 by Congress as a partnership between the DoD, Department of Energy, and the EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds fundamental research, applied research, and advanced technology development, which ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program. In this program, we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is that transition and implementation and regulatory acceptance. SERDP and ESTCP are complementary programs, with much of SERDP research occurring at the lab and pilot scale, and with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are several drivers for the type of work funded by SERDP and ESTCP, with the underlying objective of sustaining DoD ranges and facilities and their operations. This, as you can imagine, is a broad undertaking. It takes the form of looking at maritime sustainability, threatened and endangered species, climate impacts, UXO, unexploded ordnance, munitions constituents, and other environmental drivers. One key environmental driver is the reduction of current and future environmental liabilities. This involves addressing contaminations from past practices, including impacts to groundwater, soils, and sediments, UXO contamination, developing management approaches for contaminants of emerging concerns. Second part of this is pollution prevention, with a focus on eliminating chemicals of concern or hazardous materials in manufacturing, maintenance, and operations that are conducted on our installations. There are several focus areas for research and demonstration within SERDP and ESTCP, and these are listed here, and you can find them on our website too, serdp-estcp.org. SERDP and ESTCP are funding a broad range of other PFAS-related projects. You can access the PFAS program as well as using the link on this slide. The boxes along the top workshops that have been held to develop strategic plans for addressing PFAS issues. A summary report was prepared for each workshop to summarize the discussions and the identified research and demonstration and technology transfer needs. To view workshop reports, click associated boxes at the top. Each SERDP project has an associated box with a project title, which links to a full description of the project, as well as any reports that have been published as part of the project. Each ESTCP topic listed represents a single topic. Click the project title to go to that project's webpage. As mentioned earlier, technology transfer is very important within the SERDP and ESTCP programs. Technology transfer efforts include the development of videos, training workshops, and guidance documents. This webinar series is a substantial component of our technology transfer efforts. Our webinar series highlights research and demonstration efforts from all of our program areas. Upcoming topics include the use of environmental DNA to monitor population parameters on DoD lands, the detection and characterization of buried ordnance in marine environments, forecasting dry land ecosystems, vulnerability to change, and others. Registration is open for webinars through the beginning of next year. You can find additional information about upcoming webinars at this link. All past webinars are archived and can be accessed at this link as well. And finally, I want you to save the date for our 2022 SERDP and EST Symposium. That'll be held November 29th through December 2nd, Arlington, Virginia. The event will showcase latest technologies that enhance DoD's mission through improved environmental and energy performance. Hope to see you there. And back to you, Rula.
Thank you so much, Robin. It is now my pleasure to introduce our first speaker, Dr. Detlef Kanaki, who is the S. James Ellen Distinguished Professor of Civil, Construction, and Environmental Engineering at North Carolina State University. Detlef is also the Deputy Director of NC State's Center for Environmental Health Effects of PFAS. His research interests broadly encompass drinking water quality and treatment. He is a trustee of the American Water Works Association's Water Science and Research Division and an associate editor for the AWWA Water Science. Detlef is also a member of the North Carolina Secretary's Science Advisory Board. He received his bachelor's, master's, and doctoral degrees, all in civil and environmental engineering, and all from the University of Illinois at Urbana-Champaign. Detlef, please proceed.
Great. Thank you for the introduction, Rula. And my pleasure to give you an update today on our SERDP project on the thermal reactivation of spent GAC from PFAS remediation sites. I'm going to follow the standard agenda for the SERDP webinars. So I'm going to give a brief background and talk about our objectives, the technical approach, results, future work, conclusions, and benefits to the DoD. In terms of background, spent granular activated carbon can be managed through thermal reactivation. In the thermal reactivation process, the spent activated carbon undergoes at least these 3 steps that I'm showing here. First, the wet carbon is dried, and the material that is absorbed to the activated carbon is pyrolyzed in an inert atmosphere, like a nitrogen atmosphere, and then finally the activated carbon is reactivated with oxidants such as steam and or CO2. And typically this process takes place at temperatures at about 700 to 900 degrees Celsius. And off gases from this process go through an afterburner to mineralize those at very high temperatures. And I'm showing a couple of photos just to give you an idea in what types of furnaces these reactivation processes take place. So on the left here is a rotary kiln furnace, and on the right a multiple hearth furnace. Now, research that I'm presenting today will focus mostly on the pyrolysis step, because that's the step where PFAS would most likely break down, and also it's maybe the most conservative way of looking at this in terms of the formation of potential products of incomplete destruction. So in terms of our objectives, the goal is to identify conditions that effectively mineralize PFAS during the thermal reactivation of spent activated carbon. And we're interested in particular to understand the effects of reactivation temperature and time, and also the addition of calcium and pretreatment with base to see whether those processes can help with the mineralization of the PFAS that are loaded on activated carbon. The work that we've done to date has all been done in a thermal gravimetric analyzer. And so I'm going to use my mouse here to show you how this is done. So on the thermal gravimetric analyzer is a small pan that is connected to a very sensitive scale. And so here we can track mass loss as a function of temperature as the pan is inside of this furnace that is heated at a rate of 15 degrees Celsius per minute. And we are adding nitrogen at a flow of 100 milliliters per minute into this furnace. So from these data, we learn how PFAS mass loss occurs as a function of temperature, but then we're also collecting the off gases from the TGA, and we route them through an impinger system where we capture compounds that are soluble in 0.1 normal sodium hydroxide, and compounds that pass through the impinger are collected in a Summa canister where we're basically looking at volatile compounds that are produced during the thermal degradation of the PFAS. We work with different analytical methods to establish a fluorine mass balance. So we look at the pan residue on the TGA. We dissolve that in water and then use an ion selective electrode to measure fluoride. We use ion chromatography to verify the ISE results, but also track other anions and cations, and also combustion ion chromatography for total fluorine measurement. For the impingers, we're looking at the same analytical methods as for fraction 1, but also we look at liquid chromatography and mass spectrometry to look at potential products that are formed and captured in the impingers. And then this third fraction in the Summa canister is analyzed by gas chromatography and mass spectrometry in collaboration with our EPA partners. Because some of the products of incomplete destructions have higher boiling points, we're in the process of adding a fourth step here. We're routing the exhaust initially through an XAD resin to capture semi-volatile compounds, which would then also be analyzed by GCMS. So here I just want to show you what our data look like. So these are Tga scan curves for 4 perfluorocarboxylic acid sodium salts and 3 perfluoroalkyl sulfonic acid potassium salts. And we're tracking the remaining mass as a percentage of the initially added mass as a function of temperature. So how do we analyze these Tga scan curves? We're interested in when does the thermal degradation begin. So we call that the onset temperature. And when does the thermal degradation end? And we call that the end-set temperature. And the software in the instrument gives us those by extrapolating the horizontal plateaus here and the line that's tangential to the inflection point, and that those result in intersections for the onset and end-set temperatures. So if we look at all the perfluoroalkyl carboxylic acid salts that we looked at here, we have a 4-carbon perfluorobutanoic acid, 5-carbon pentanoic, 6-carbon hexanoic, and 8-carbon octanoic acid in the sodium form. And we can see that the onset temperatures are not strongly chain length dependent here. All of these salts begin to degrade between about 260 and 275 Celsius, and the degradation is complete between about 290 and 295 degrees Celsius. When we look at the sulfonic acid salts in the potassium form, the onset temperature is substantially higher, on the order of 460 to 470 degrees Celsius. And then we have this kind of two-step behavior for degradation that we're still trying to understand better. But the end-set temperature for the sulfonic acids isn't until about 700 degrees Celsius. So when we look at all of these Tga scan curves together, you can see all the carboxylic acids cluster together, and then all the sulfonic acids cluster together with relatively little chain length dependence. We were also interested in understanding differences in the thermal behavior between PFOA and Pfos in their acid and salt forms. So here I'm comparing Tga scan curves for PFOA in the acid form and PFOA in the potassium form. And you can see that the potassium form degrades at a higher temperature, and the end-set temperature was about 170 degrees Celsius higher for the salt compared to the acid. And we see something more dramatic even for the PFOS comparison here, where PFOS in the potassium form degrades at a temperature that's substantially higher than that of the acid form, with the end-set temperature being more than 500 degrees Celsius higher for potassium, for the potassium salt. So when we look at what we're capturing in the impingers from an overall fluorine mass balance perspective, we're really not finding much. So here are the percent recoveries of fluorine after we degraded PFOA in the acid form. And you can see we form a little bit of PFHXA and PFPEA and PFBA, but the sum total is less than 2% of what we added. When we degraded perfluorooctanoic acid in the potassium form, we also see very little recovery of fluorine in the form of the smaller carboxylic acids. Here we did form a little bit of the heptanoic acid. When we did the same experiment with PFOA in the sodium form, we found very little. So this highlights it's important in which form the PFOA is actually in when it degrades thermally. And for quality control purposes, I'm showing also the blank here. So then the question is, where does the fluorine really go? Here I'm introducing now experiments where we look at PFOA in the potassium form, either alone or in the presence of calcium hydroxide. And we wanted to see, does the addition of calcium hydroxide change our fluorine recovery? And here for PFOA, we see that if we have PFOA in the absence of lime, the primary fluorine that we were able to recover in the mineralized form was in the form of potassium fluoride residual on the Tga pan. And when we added calcium hydroxide, we formed a little bit more fluoride, perhaps as a result of the lime degradation that supported a little bit of mineralization. So we formed some calcium fluoride as shown in blue here. But still, we're only capturing about 20% of the initially added fluorine in the form of fluoride. Things are quite different when we look at PFOS in the potassium form in the absence and presence of calcium hydroxide. And here we see that calcium hydroxide dramatically enhances PFOS mineralization. And we looked at different calcium to fluorine molar ratios here, and we see that at the highest calcium to fluorine ratio, we capture over 80% of the initially added fluorine in the form of mostly calcium fluoride with small amounts of potassium fluoride and hydrogen fluoride. We think this enhanced mineralization for PFOS is a result of the similar onset temperatures for lime and PFOS degradation, and the liberation of water or steam at this temperature as calcium hydroxide is being converted to calcium oxide, and the steam then is enhancing the mineralization of the PFOS. So next, we looked at mixing PFOA and PFOS with sodium hydroxide, and here are results for PFOA in the potassium form. And here we see that the presence of NaOH really did nothing to enhance PFOA mineralization. But when we look at PFOS, again, we see that the addition of sodium hydroxide here now enhances mineralization and actually shifted the onset temperature from pure PFOS in the potassium form as shown here to the PFOS NaOH mixture to the left. So when we look at when does sodium hydroxide degrade, it degrades at around 300 degrees Celsius. And coincident with the degradation of sodium hydroxide, we found that PFOS began to also degrade here. Again, we think this is at least in part a result of the release of water as sodium hydroxide is degrading. And the sodium hydroxide degrades to a number of different products based on the papers we've been reading, including sodium oxide, sodium peroxide, and sodium hydride. When we added calcium chloride or sodium chloride to either PFOA potassium or PFOS sodium salts, we really saw no impact on mineralization, and in all cases, the fluoride recoveries were less than 10% of the initially added fluorine. Also, we're interested in how natural organic matter impacts PFOS mineralization, because on activated carbon, the largest percentage of adsorbed substance in many cases is the natural organic matter. And so here I'm just showing an early result for a mixture of PFOS and natural organic matter. And for natural organic matter, we're using Suwannee River natural organic matter. This is natural organic matter that's been isolated by reverse osmosis, and it does have some calcium content. So here, when we look at PFOS alone and the fluorine recovery in the form of different inorganic fluorides, we see very little recovery. But once we mix the PFOS with natural organic matter, we see an increase in mineralization, and we think that is a result of the continued degradation of the natural organic matter as we increase temperature and the liberation of hydrogen in some form, whether that's water or some other compound that contains hydrogen that can support the formation of HF and the mineralization of the PFOS. So in many cases, I've shown you now that our mineralization was well below 100%. So then the question is, where does all the fluorine go? And so we've been working closely with scientists at EPA here in Research Triangle Park in North Carolina to look at what compounds are we capturing in the SUMA canisters. And initially, we did this work with the shortest chain PFAS that we're looking at. So for the carboxylic acids, Pfba, and for the sulfonic acids, Pfds. And here I want to draw your attention primarily to the bar chart where the SUMA results are shown. So for Pfba, very consistently, whether we degrade Pfba alone or in the presence of lime or sodium hydroxide, we capture about 2/3 of the fluorine in the SUMA canister. So a lot of volatile organic fluorine compounds are formed as we're degrading Pfba. When we look at Pfbs, and again, we're here looking at targeted results from the SUMA can, it's quite different. We're only capturing somewhere around 10% of the compounds that are targeted by the GCMS method. So what compounds are we finding in the SUMA canister? So when we look at Pfba degradation, and we look at Pfba here in the sodium form, consistent with a paper that was actually published in the 1950s, we see that the dominant product is hexafluoropropene. So we split off the carboxylic acid group, and then we have an elimination of one fluorine at the beta position here to form this hexafluoropropene. We also form a little bit of 1H heptafluoropropane, which means there must have been a little bit of hydrogen around for this reaction to occur. And we also formed a little bit of tetrafluoroethylene. The non-target analysis that was done on this sample as well did not show any additional identifiable organic fluorine products. For Pfbs, things are quite a bit messier. So we found through targeted analysis 6 different compounds, and the dominant among those was perfluorooctane, which I thought was very interesting because this suggests we're basically breaking the sulfonic acid group off and then have a 4-carbon fluorine radical, and 2 of those can combine to form this perfluorooctane. So here's an example where we're actually forming a larger product of incomplete destruction from the PFBS. What I showed you on the previous slide, though, was that the total of all of these compounds that we detected by targeted analysis made up about only 10% of the fluorine that was added in the form of PFBS to the TGA pan. So through non-target analysis, additional compounds were identified that were present in substantial quantity based on the peak areas that were observed, and these include octafluoro-2-butene and octafluoro-1-butene. So these 2 compounds suggest that an important pathway for PFBS degradation is similar to one that we see for PFBA, where this sulfonic acid in this case is broken off, and then we have what seems to be either beta or gamma elimination of a fluorine. So how about activated carbon? So far, all the experiments that I've shown you were conducted with PFAS in the absence of activated carbon. So now we loaded PFAS to activated carbon, and one question we had in the beginning was, well, in which form does the PFAS actually absorb? Is it the acid form or is it the potassium form if we dose the PFAS as a potassium salt? So we tracked for both PFOA in the potassium form and PFOS in the potassium form the uptake of the anion in green and the uptake of potassium in this peach color. And we see that for PFOA, more than half of the PFOA absorbed as the potassium salt, whereas for Pfos, it was more in the order of a third, meaning we have perhaps on the activated carbon then a mixture of PFOA in the acid and salt forms, and similarly for PFOS in the acid and in the salt forms. And that will most likely have an impact on how these compounds degrade on the activated carbon. So for PFOA here, we looked at degradation of just activated carbon alone and then loaded activated carbon. And then we normalize these curves by subtracting out the activated carbon blank. And then we basically get here in the red a curve that shows how PFOA degraded on activated carbon. And we can compare that to PFOA alone in the acid form and PFOA in the potassium form. And so what we see is that, onset of PFOA degradation occurs at temperatures below those seen for PFOA in the potassium form, meaning that probably some of the PFOA in the acid form began to degrade at a lower temperature. But then we also see that PFOA degradation continues well beyond the onset temperatures that we saw either for the acid or for the salt alone. And this may be related to mass transfer limitations, for example, for these products to diffuse out of the GAC pore structure. For PFOS, we see something similar. When we look at PFOS acid and PFOS salt, then the absorbed PFOS degrades at a temperature that's somewhat below that of the salt, so suggesting that some of the acid might have begun to degrade at this lower temperature. But we also see that PFAS degradation continues beyond the 800 degrees C mark. And we also see that after normalization, we actually get into negative territory, which is something we're trying to still understand. You know, this suggests that maybe some of the products that are formed as the PFOS is degrading are either reacting with the activated carbon base, or that the behavior of activated carbon, the thermal behavior of activated carbon when it's loaded up with PFOS, is somewhat different from the degradation behavior of the activated carbon blank that we're looking at. So in maybe what I want to mention for the activated carbon experiments is, without the addition of any base, mineralization of the Pfoa and Pfos was minimal, and less than 3.5% of the added fluorine was captured in the form of fluoride. So that means we need to do additional work to find out how we can really enhance the mineralization of the loaded PFAS on the activated carbon through, for example, the addition of base. So for future work, we will conduct additional TGA experiments with PFAS-loaded activated carbon in the presence of salt and base mixtures. We'll continue our collaboration with EPA to further enhance our fluorine mass balance, for example, through the addition of the XAD resin trap, and then scale up our TGA experiments to bench scale fluidized bed furnace experiments. And so what we found was that in the absence of GAC, the thermolysis of all tested PFAS was complete at temperatures used to reactivate activated carbon. But in the presence of GAC, the thermolysis of absorbed PFOA and PFOS was not complete at a temperature of 800 degrees Celsius. So, that is something we are looking into more to really understand what temperatures are needed for full mineralization. It appears that the addition of lime and sodium hydroxide can enhance the mineralization of some, but not all, of the PFAS we're studying. And similarly, the presence of natural organic matter can enhance the mineralization of PFOA and PFOS salts. In terms of benefits to the DoD, we developed an experimental approach to assess PFAS mineralization during thermal processes. And we also developed techniques to identify potential products of incomplete destruction. We also are developing data that will allow whether PFAS-laden GAC can be safely reactivated. And if that is the case, the use of reactivated GAC can lower remediation costs at PFAS-impacted sites compared to single-use GAC. With that, I'll turn it over to you, Rula.
Great, thank you. Questions are coming in very fast. We'll start with this one for you, please. What levels of PFAS loading can be expected on spent GAC? And are you using that range of concentrations in your experiments in the lab?
Mm-hmm. Yeah, so the levels will depend strongly on two things, the influent PFAS concentration and also the GAC service life. So we've done some back of the envelope calculations here, like, for example, if you had an influent PFAS concentration of 100 nanograms per liter and your GAC bed lasts 50,000 bed volumes, then the PFAS loading on the activated carbon would be on the order of 10 micrograms per gram, or 10 parts per million, if you want to express it that way. So these are relatively low levels. Another way to look at this is, like if a vessel holds 10,000 pounds, you would have 0.1 pounds of PFAS on the activated carbon, which would be like 45 grams. In our experiments, we're using much higher concentrations on the order of a 10% loading right now, because otherwise we wouldn't be able to track the mass losses that are associated with the PFAS in our TGA experiments. So that is, perhaps a limitation of the work we're doing, but if we don't use these higher loadings, we cannot really address the mass balance portion of our research at all.
Thank you so much. This next question is from Marquette University. Should higher recovery of PFAS in the presence of natural organic matter also be facilitated due to the absorption of PFAS on NOM through hydrophobic interaction, in addition to NOM degradation?
Well, that's a good question. I think that the association of the anionic PFAS with NOM is in most cases relatively minor, and just because of electrostatic repulsion, right? We have, NOM carries a lot of negative surface charge, and the perfluoroalkyl acids that we're studying are negatively charged. So I think the PFAS probably absorb at absorption sites that differ from those where most of the NOM absorbs. But yeah, it's an interesting question whether maybe the configuration of a PFAS associated with an NOM compound molecule would change, and therefore the thermal behavior would change. But I'm actually thinking that the same question would apply when PFAS absorbs to the activated carbon graphitic platelets. Maybe the molecular geometry changes, and as a result, maybe the thermal behavior could change a little bit.
Thank you. This next question is from Florida International University. Do you have any plans to look at other compounds and test other compounds in sodium and calcium hydroxide to see if they could enhance mineralization versus degradation to incomplete byproducts?
So right now, given the complexity of the analytics, we're really focusing on PFOA and PFOS, but we have included in our analyte list also 6,2-FTS, for example, and I showed some results for shorter chain PFAS. But yeah, this is a limited scope project, so far we have limited our efforts really to PFOA and PFOS. But yeah, it's important to address other subclasses, for example, zwitterionic compounds and telomere acids, maybe some fluoroethers, to be comprehensive, to understand how different PFAS structures also influence their thermal behavior.
Thank you. And two quick questions before we transition to the second speaker. The first one is from Temple University, particularly on slide 31, but throughout your presentation, you referred to mineralization, which is the complete degradation or defluorination of the PFAS molecules, versus mineralization. But on slide 31, you said that short chain compounds were produced during the degradation of the Pfoa and Pfba in that particular set of experiments that left?
You cut out there for a second, Rula. So I'm going to slide 31. I think maybe it's 32 where I'm showing the carboxylic acids here. Can you repeat the question, because you were cutting out when the key part was being asked?
The individual from Temple University was asking whether you measured the byproducts that were produced during the degradation of PFOA.
So we have so far looked at, maybe if we go instead to the TGA setup at the very beginning, maybe slide 4. So far we've looked at fractions 1, 2, and 3 for compounds like PFBA and PFBS. And so we find that fraction 2 is relatively minor, and that the key fractions are fractions 1 and 3 so far, where we're looking at the Summa canister and the pan residue. Yeah, like this one would be perfect. So, fractions 1 and 3 are the key ones. Fraction 2, so far we have identified really only a small fraction of the initially added fluorine.
Thank you. And just to conclude, there's a question from one of the attendees. Should water utilities, which are using granule activated carbon to treat PFAS and then sending it for reactivation, be concerned that the reactivation process isn't fully destroying PFOA and PFOS based on your work? Do you have any advice for water utilities?
Yes. So we're pretty confident that PFOA and PFOS will be completely destroyed. But what I mean by that is that you won't find any more PFOA or PFOS on your activated carbon. What we're still interested in is, are there any products of the PFOA or PFOS degradation that may stay behind on the activated carbon? I think the likelihood that organic fluorine will be staying behind on the activated carbon is very low. But I think one thing that might need some attention is potential leaching of fluoride from the reactivated product. And that could be either in the form of readily soluble fluoride salts like sodium fluoride or potassium fluoride, which could be easily rinsed out after the reactivation process. Or there could be some calcium fluoride there, which is very poorly soluble. And yeah, I don't know whether it would be a concern or not. So that's something we need to still understand as well. But from an organic fluorine perspective, I would say it's based on all the results that we're seeing. The organic fluorine most likely will be gone. Although, like I showed on the last couple slides, we may need high temperatures or additional time compared to what we're using in the TGA to completely diffuse all of the products that we're forming out of the GAC pore structure. So that's still work that we need to do to really fully be able to answer that question.
Thank you so much for a great presentation. We'll get back to answering additional questions for you, Detlef, if we have time towards the end of the webinar. At this point, we're going to transition to our final talk today. It is my pleasure to introduce Dr. Braden Giordano, who is a research chemist at the U.S. Naval Research Lab in Washington, D.C. Braden serves as the head of the Chemical Sensing and Fuel Technology section in the Navy Technology Center for Safety and Survivability. He has served as a principal and co-investigator for projects funded by SERDP, the Office of Naval Research, the Defense Threat Reduction Agency, and the Department of Homeland Security. Braden has authored over 40 peer-reviewed papers and book chapters and has delivered over 100 technical presentations. His interest in developing replacements for AFFF comes from his experience in developing micelle-based separation media for electrophoresis applications. Braden received a bachelor's degree in chemistry from the University of Richmond and a doctoral degree in chemistry from the University of Virginia. Braden, please proceed.
Thank you very much, and I'd like to thank the organizers for allowing me to talk about our efforts on developing a polyethylene oxide-based polymer formulation for PFAS-Free fire suppression. Briefly, the talk is broken up into discussing the objective and research context of what we're doing, our approach, some results, conclusions, and then ultimately benefits to the DoD. Our goal in this work is to synthesize and characterize polyethylene oxide-based polymers as drop-in replacements for aqueous film-forming foams. We've chosen to use reversible addition fragmentation chain transfer polymerization to functionalize the hydrophilic polyethylene oxide with hydrophobic tail groups. We perform a laboratory scale evaluations to determine firefighting capabilities, and ultimately, at the end of this program, we'll transition to full-scale testing. Some context, AFFF formulations must be per and polyfluoro or PFAS-free by October of 2023 for shore-based applications. One of the underlying reasons why we chose to work with something like PEO is because there's a desire for drop-in replacements and thus minimally impacting AFFF storage and delivery systems. This is where you might consider something like viscosity an issue, and why we thought PEO might be a very useful tool in that it is readily soluble in water and doesn't contribute significantly at low weight percentage to viscosity. We chose raft-based synthesis because it limits the synthetic steps and thus the person cost of synthesis. They're generally high yield and scalable. And there's an existing knowledge base with PEO-based polymers due to their use in the pharmaceutical and cosmetic industry as it relates to safety within the environment and with people. So our general approach here is focused on the initial synthesis and evaluation of the polyethylene oxide polymers, followed by screening with laboratory-based tests that look at foam performance and firefighting performance on the small scale level. Once we understand how our synthetic approach is affecting what's happening in the screening phase, we then iteratively look at revisiting the synthesis. So there's a feedback loop here as we're developing the best possible PEO-based polymer. Once we have a polymer that meets a certain series of metrics and we think has value in scaling up and doing a full-scale test, we will then transition to a full-scale test associated with the mil spec. We've gone through 3 synthetic approaches that result in polyethylene oxide-based polymers. One is a linear block polymer, where the hydrophilic chain is polyethylene oxide is a single long chain, and we use the raft synthesis to create a hydrophobic comb on its end. Optionally, there's a comb statistical polymer where all of the components are placed in a single pot together, and a comb polymer is formed that has the random addition of either the hydrophilic PEO group or our hydrophobic chain. Alternatively, there's a comb block polymer where we generate a comb polymer that is exclusively polyethylene oxide based, and we couple it to hydrophobic chain comb polymer that's, of course, exclusively hydrophobic. As you can tell just by looking at this picture, there's quite a bit of knobs we can turn with respect to the synthesis process, including the length of the hydrophilic chain, the terminal functionality of the hydrophobic chain that would be right here, obviously the nature of the hydrophobic groups, and then, of course, the length or relative abundance of hydrophobic to hydrophilic groups in the chain. So there's a lot that we can do with this chemistry, but not overly complicate the synthetic approach because of the versatility of the raft synthesis process. Our standard method for synthesis conformation is to perform the synthesis and do NMR and gel permeation chromatography GPC to verify the purity of the final product and successful integration of the functional groups within the synthesis. We also utilize the GPC to give us additional insight as to the molecular weight and monodispersity of the final product. And so these are just examples of some of the NMR data that we receive from butyl acrylate functionalized polyethylene oxide and lauryl acrylate functionalized polyethylene oxide. Once we have the product, we go through a series of laboratory-based measurements to characterize the synthesis product. We look at solubility in aqueous solution, surface tension, critical micelle concentration. We also generate foams with that material and look at its behavior using a dynamic foam analyzer. In that work, we can quantify the liquid drainage rate and also get a sense as foam structure in the form of bubble diameter. These tests get progressively more complicated and progressively more like fighting a fire. We look at degradation of foams over heated fuel. This picture shows a foam over a heated heptane solution. We look at foam height as a function of time. We're trying to simulate in this test the interaction that a foam is going to have with the vapors associated with a fuel fire. And as you'll see with some of the data we're collecting, interaction of a foam with a fuel can be a significant contributor to its behavior, and just basing conclusions on how a material foams in the absence of interaction with a fuel might not necessarily tell you everything you need to know about that foam's performance in fighting a fire. And then finally, we do a small scale test where we generate a 19 centimeter diameter pool fire and attempt to put out that fire with our foam formulation. So over the course of this work, we've had the opportunity to turn quite a few of the knobs associated with the synthetic process. And so what I'm going to show in the next several slides are just some examples of how we have evaluated and turned some of those knobs. And so in this slide, what we're looking at is a series of comb statistical polymers where we are varying the hydrophobic chemical structure. We're looking at lauryl, butyl, cyclohexyl, benzyl, and tetrahydrofuryl hydrophobic moieties. And what we're seeing in this work as the general trend is that the alkyl-based hydrophobic groups are providing the best overall foam volume or foam height maintenance as a function of time. Whereas when we start to tweak that away from the alkyl and look at something like the tetrahydrofufuryl, it effectively is not maintaining its volume or its height during that testing. One thing that's interesting here is that as we're taking all of these measurements, we're trying to figure out if some simple measurements are going to tell us anything about foam volume or foam height or other properties that might be important as it relates to firefighting. Surface tension and critical micelle concentration could sometimes be useful for that, but what we have found for these types of polymers is that the surface tension and the critical micelle concentrations do not necessarily relate to foam stability as a function of time. The other property that we're measuring using the dynamic foam analyzer is the drainage rate. And what we're seeing is that independent of the hydrophobic functional group that we've put on there, we are not seeing a significant variability with respect to the drainage rate. The other, part of that coin is realizing that the drainage rate and the foam height or foam volume are not necessarily related to one another, which we find interesting at times. You would generally expect that the more water that you maintained within the foam, the more stable that foam would be, and we're not seeing that in our efforts. We've also looked at the polyethylene oxide molecular weight and its terminating functionality. And so in this work, we're looking at two collections of data. The first is looking at the effect that the polyethylene oxide terminating group has. So in this instance, we have two types. We have one that terminates with a methoxy group, and then we also have one that terminates just with a hydroxy group. And what we see is in this example that the material is also varying, also varying as a function of the molecular weight of the polyethylene oxide. So we have a series that has 200, 400, and 1,000 molecular weight polyethylene oxide with a methoxy terminating group. And then we have a 200 and 400 molecular weight polyethylene oxide terminating just with the hydroxyl group. And they all share the same butyl acrylate hydrophobic group. And what we're seeing in this data is that there is some dependence on foam lifetime as it relates to the molecular weight of polyethylene oxide. With respect to the methoxy-related group, the 200 molecular weight is not nearly as stable as the others in this series, which allows us to gravitate towards heavier polyethylene glycols, oxides. But again, as was the case with polyethylene oxide differences with respect to the hydrophobic group, there's little difference in drainage rates as a function of the molecular weight of polyethylene oxide or its terminating group. So now we transition to the fuel-induced foam lifetimes. In this work, we are adding our polyethylene oxide-based polymers to a 5% solution of glucopon 2,2,5-DK, and we're assessing its foam lifetime of a 4-centimeter foam layer above heptane that's heated to 60 degrees. Glucopon 2,2,5 is an environmentally friendly common hydrocarbon surfactant in firefighting foams. Our foam lifetime is based upon the complete degradation from the heated fuel on the surface of the heptane. So in this work that I'm showing here, we're looking at the hydroxy-terminated polyethylene glycol-based polymers and methoxy-terminated polymers. And what we found here, which was a bit different from the behavior we were seeing in the absence of fuel, is that the methoxy-terminated polyethylene glycols tended to be more stable. not as stable as the glucopon 225 by itself, but more stable relative to one another. Additionally, we looked at statistical and block polymers, and what we found in this work, well, we found quite a lot of things, but what was very interesting to us is how the different types of polymers worked in a different weight % range. And so we found generally with our statistical polymers, regardless of the terminating group, whether it was something like lauryl acrylate or butyl acrylate, whether it had a methoxy or a hydroxy terminating group, or the relative ratio of hydrophilic to hydrophobic, when we were working exclusively with statistical polymers, they gave their best results at lower weight percents in the solution of glucopon 225, whereas when we worked with block polymers that sort of segregate all the polyethylene oxide from the hydrophobic group, those worked in much higher weight percentages. Now, this is interesting in part because as we get into these higher weight percentages, we might start running into situations where the viscosity of this solution becomes something that wouldn't allow for it to become a drop-in replacement, which is one of the guiding principles of why we are attacking this problem with this sort of synthesis process. So one of the things that we've learned in this work is that polymer or additive interaction, polyethylene oxide interaction, is something that we really need to pay very close attention to. And to give you a sense as to how, one, complicated this process is and what our focus in research is moving forward, is to just look at the effect that the polyethylene oxide additive has on some common surfactants and formulations that have been put together here at NRL. So when we add a polyethylene oxide-based additive to the glucopon 225, we find that its presence at a 0.0625 weight percent is destabilizing of the glucopon. When we add it to a different siloxane-based surfactant, 502W, or to Triton X100, which is a common surfactant, we see that it improves the stability. But when we look at a mixture of surfactants that NRL has developed that includes 502W and glucopon 225, we see that it is very destabilizing and more destabilizing than it was to the individual components. This sort of effort has caused us to focus our evaluation of our polyethylene oxide-based polymers on interaction with the glucopon 225 component. And we deem a candidate good as an additive when we see minimized disruption in the glucopon 225 foam lifetime. We do take these polymers all the way to small-scale fire testing. And so we have an example of a few different, well, the same but different scaled syntheses of polyethylene oxide-based polymers. So in this top trace, we have the CO2 concentration measured over a heptane flame. And as we initiate the fire, we see that the CO2 concentration is increasing. At this point, indicated by the black line, we are beginning to apply the foam. And what we are seeing here is an initial spike of the CO2 concentration, which is expected as the foam is covering the flame. There's an increase in flame velocity, and so the CO2 spikes. And then we expect to see a decrease. Successful fighting of the fire would see this restore to the basal CO2 concentration. We are seeing some fire suppression, but we are not seeing the fire go out as we are still seeing CO2 there. We go to a much more complicated gasoline-based fire, and we're not seeing nearly as effective even suppression of this fire. We can still see the CO2 is slightly rising. This goes back to some of the efforts we were sharing before. Gasoline is a much more complicated vapor. It's a much more complicated composition relative to heptane, and so there are certain components in the gasoline that are really adversely affecting the foam, and thus we're seeing very poor suppression. In this last slide, as we take a closer look at the heptane metrics, we're also taking a look at how the synthesis scale may or may not affect the final product. And so we have two syntheses that involve the use of 400 molecular weight methoxy-terminated polyethylene oxide with a lauryl acrylate hydrophobic group, and we did a 5-gram scale synthesis and a 90-gram scale synthesis. And what we're seeing in this table is a comparison between those results. And so we have the expansion ratio highlighted here, and we see that the addition of our polyethylene oxide is slightly increasing the expansion ratio, but we're not seeing a significant difference between the two scaled syntheses of the LB99 and the LB95B relative to one another. So that is that sort of information, along with all of the supporting information that verified the synthesis product, is telling us that the scale is not adversely affecting or changing the final product. We're also seeing consistent coverage times, though the addition of the polyethylene oxide to this mixture is decreasing the coverage rate or increasing the time necessary to fully cover the 19-centimeter pool fire. So some quick conclusions and paths forward. The polyethylene oxide polymer synthesis by the RAFF does offer a robust path towards a PFAS-free alternative, primarily due to its tunability and scalability. This iterative approach has allowed us to tailor the kind of syntheses that we are working on, including selecting the appropriate molecular weight and terminal group of the polyethylene oxide and working with the appropriate hydrophobic group. We have seen in recent data a total reduction of the molecular weight is advantageous, and what we're focused on right now is adjusting the hydrophobic to hydrophilic ratio in order to promote the most stable molecular weight. Another interesting note that I didn't get into is that whether this work or these solutions are prepared in deionized water or seawater is not changing the overall result. So the presence of seawater is not disrupting the additive's performance or adding more complexity to how the additive is working. The benefits we see to the DoD is that this can serve as a drop-in replacement for AFFF formulations, primarily due to its low viscosity. We see this as a low-cost, scalable synthesis pathway, and because of its history of use in the pharmaceutical and cosmetic industry, we look at this as moving towards a lower health risk relative to PFAS. I'd like to acknowledge my co-workers in this program, including Grant Daniels, Catherine Hinnett, Nicholas Weiss, Lauren Brown, and Stephanie Vaughn. And with that, I'd be happy to answer any questions.
Thank you so much, Braden. We have received a number of questions. The first one is from ADA Technologies. If your formulations are intended as drop-in replacements for AFFF, how comparable is the viscosity relative to AFFF for utilization of current inline mixing devices for delivery?
At this, our goal is to have something that is going to be of comparable viscosity. We've evaluated in excess of 100 different polyethylene oxide products. We have certainly found some that are not compatible, and we discount them at this point. So anything we're working with would be usable in as a drop-in replacement at this point.
Thank you. And this is a question from the NRDC, or the National Resources Defense Council. On one of your slides, slide 54, you showed the approach for developing the new PFAS-free fire suppression polymers. At what point in this approach would you expect the health, toxicological, and safety aspects be evaluated?
That is not formally part of our program, but as we get to items, as we have items that are transitionable to the large-scale testing, we would then approach other groups to evaluate those from a health and safety standpoint, and use other collaborations to get at that.
Thank you. This next question is from Bloomberg. Can you elaborate on the function of the combs that you mentioned also on slide 55?
I'm sorry, on the comb?
Yes. What is
so,
the function of the combs?
So that's just the nature of how these hydrophobic chains are defined. We have a acrylate-based group, and the way that we can add more or less hydrophobicity or hydrophilicity is to use this acrylate terminating group on the hydrophobic molecule to extend that. And so when we manipulate molecular weight or we manipulate ratios, we are adding tines, I believe they are called, to the comb. And so our final product, we can target how many, the number of butyl acrylate or lauryl acrylate molecule monomers that are on the final component. So that's a knob that we can turn as we're optimizing this synthesis pathway towards a final product.
Thank you so much. This next question is from Surfactive Corporation. Have you looked at the stability of the ester links in the polymer over time?
I would say that we have probably done that informally, where we've evaluated a foam and then looked at it at some later time. And what we have noticed is that materials that have been sitting on the shelf for months are seeing no change in overall performance or destabilization as a function of time. Polyethylene oxide molecules tend to be pretty stable in solution, and we're not seeing any disruption at this point.
Thank you. Another question related to toxicity. You did mention that PEO has a lower health risk compared to PFAS. Can you elaborate based on studies others have done, based on what is published in the literature, based on your own work? Can you please elaborate on that?
Well, that's just based upon work that others have done. Those tend to be localized in the pharmaceutical industry because polyethylene oxide-based materials are often used in pharmaceuticals like cosmetics. We might, if you have children, be very familiar with a very common polyethylene oxide-based product called Miralax, which is an osmotic laxative that is often utilized, and all that is a long-chain polyethylene oxide-based polymer. And my understanding is polyethylene oxide is actually a component in COVID vaccines as well. So there's quite a bit of literature associated with polyethylene oxide-based health effects.
Great. And beyond the health effects, do we know anything about the environmental risk profile for PEO? Is there enough in the literature if folks are interested?
There's been some studies. I'm not entirely familiar with all of them, but there have been some studies on the environmental effects. I would have to dig a little bit to provide specific references to that. But I would expect, you know, it's a much more readily accessible carbon source from a degradation standpoint. If you were thinking about something like naturally occurring biomes, treating the polyethylene oxide as a available carbon source than say something like a PFAS component, which would be resistant to natural degradation techniques.
Great. All right, and this next question came from an anonymous attendee, and it's a really important question. In terms of a timeline, could some of the components that you're developing be commercialized in time for the deployment of PFAS-free forms by 2023? How does this work in the bigger scheme of things with DoD's timeline?
That is a question that might be a little bit above our pay grade here at the bench level, but the scalability of the technique was intended to provide for that if possible. That was something that we did have in the back of our mind when we notionalized this proposal in the first place. Can we develop a synthetic route that is easy and robust, transferable outside of our local research environment to the point where it can be implemented on a scale necessary to provide for the DoD needs?
That's fair. One last question came in from ABA Technologies. Do you believe that there is any value in using molecular dynamic simulations to evaluate different molecules before moving to benchtop testing, or is the system too complex to model?
Well, I would say that the fuel interaction is so important that any application like that would really have to have a firm understanding of the fuel's role in that behavior. I think even our own work showed even the simplest test, just looking at foam stability, isn't enough because of the intrinsic relationship that performance is going to have with that fuel. If models can take into account how the fuel is interacting, then absolutely use those kind of, and this is just my personal opinion, use those techniques to supplement the design process. But if we're looking at structure on an island by itself, I'm not necessarily certain that that is going to get us to the answer any faster. We still have to collect data that involves foam interacting with a fuel.
Thank you so much, Braden. And just to wrap up, a question for you and for Detlef. What is the last message you would like to leave the audience with today regarding your work? And we'll start with you, Braden.
Well, that's a tough question. Just that, you know, this process does take time. It is research. I think we are all desperate to have a readily available solution to the problem. We are working that problem. We understand a lot about this system, and we have a very clear path forward that we're confident is going to end in an appropriate result, which is finding a replacement for PFAS in our firefighting foams and keeping our infrastructure and our soldiers safe from the risk of fires.
That's a very important takeaway message. And Detlef, for your section, any concluding remarks?
And I had a very similar thought. You know, it turns out that PFAS remediation is really so difficult because of the persistence of PFAS, and you know, we really need to focus on pollution prevention and efforts to eliminate PFAS inputs into the environment in the first place.
Thank you. Well, I'd like to thank you both for a phenomenal webinar. At this time, I'd like to remind all of you that our next webinar on Thursday, October 6th, will be on DoD-funded research efforts to enhance and expand the use of environmental DNA, or eDNA, as a species conservation and management tool. This webinar will feature two speakers, Dr. Karen Goldberg from Washington State University and Dr. Jennifer Tank from the University of Notre Dame. Registration is open, so please visit the SERDP and ESTCP webinar webpage to register for this and other webinars through the beginning of 2023. Before we conclude, just to echo Robin's remarks, the audio and a copy of the presentation of today's session will be archived on the webinar webpage in case you would like to refer to them in the future. We would really appreciate it at this time if you can please take a moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for joining.